Hello class. Here I have a flask of boiling water. I'm going to take this boiling water, I'm going to pull it off of the hot plate here. We're going to give it a second or two for it to cool down a little bit. I want it to stop boiling. Alright, there it stopped boiling, so I'm actually going to now put a rubber stopper into it and put it in there nice and tight. And now what I'm going to do is I'm going to invert this flask, and again, it's stopped boiling, right? You cannot see the liquid boiling at all. And I'm going to put it inside this ring stand here. Now, what do you think is going to happen when I pour this cold water over it? This is ice cold water. We got, 5, 6 ice cubes in here. It is extremely cold. Now, when I pour it over this flask, I bet you a lot of you are thinking it's going to cool down. It's going to not boil at all. But when we pour the water over it, you're going to see that Mr. Selt's a little magic here. Give it a second. There we go. It starts to boil vigorously yet again. Right? If I don't pour cold water on it, it'll calm down eventually. It'll stop boiling. And then let's now add more cold water. Look at that, it's boiling vigorously yet again. So I've caused this water to boil by making it colder. How and why does that happen? Okay, so before I'm able to answer that question, first we need to understand what evaporation is. Remember, vaporization is the conversion, the phase change from a liquid to a gas. Evaporation is vaporization at the surface of the liquid. Only at the surface, nowhere else. That is evaporation. Now, most of you have an intuitive idea about evaporation, right? If you had a glass of water on your front deck, nice, beautiful, sunny day, it's going to evaporate eventually. But if you dump that glass out on your deck and it spreads out, is it going to evaporate faster? Yeah, of course it will. Why? Right? So those are some of the questions we're going to be answering today. Now, substances that evaporate quickly, we call those volatile, and they typically have low IMFs. So the lower your IMF, the faster your substance will evaporate. So let me ask you a question. What would evaporate faster? Octane or water? Octane is one of the main ingredients in gasoline. Its chemical formula is C8H18. It is a hydrocarbon. What do you think? Well, octane is nonpolar. So what is the only IMF present within nonpolar compounds? Right, that's LDFs, London dispersion forces, which are very weak in terms of IMFs. What about water? What's that got going on? Well, it has hydrogen bonding going on. It has very high IMFs. Hence, octane, despite the fact that it is a much more massive molecule, it has a much higher volatility. It evaporates much more readily, and that's because it has a much lower IMF. So here we can see our substance here, and at the surface it is turning to a vapor. And we're going to come back to this in a second, this little illustration here, because as these particles evaporate, right here we have a container lid, if you will. And what's going to happen? Well, those particles, as they evaporate, they're going to hit the container lid, and that's going to exert a pressure. So remember that. We're going to come back to that. So before I talk about the process of evaporation, let's go back quickly to these Boltzmann distributions. Right? When we have a chunk of molecules, are they all at the same kinetic energy? And the answer is no, right? There is a distribution of kinetic energies, and the average would be representative of the temperature of those particles. Now, I've shaded here this little gray section, okay? And this little gray section here represents the particles that have enough kinetic energy to change phases and become a gas. So here you'll notice that the colder substance doesn't have as many particles that are able to become a gas, whereas our hotter substance has much more particles that are able to become a gas. What do you think is going to happen to your evaporation rate as we increase the temperature? Think about that. Think about that. Now, evaporation. So you could have, for example, here a particle at the surface, and let's say that it doesn't have enough kinetic energy for a moment. And here's our little beaker here. And here's our surface of our liquid. And here's our particle. Now let's say it doesn't have enough kinetic energy. But all of a sudden, a fast-moving particle here comes along and collides with it and gives it a little bump, increasing its speed, its kinetic energy. Now it has enough to leave and enter the gaseous phase, and it can do that. So it can leave and become now a gas. Now, as it becomes a gas, the flip side could happen. It could collide with a particle in the air, right? It can collide with another particle in the air, and it can lose enough kinetic energy where it'll become a liquid yet again. Now, this is essentially how evaporation happens, right? If you have a particle with enough kinetic energy at the surface of your liquid, it can leave and it can become a gas. But why does this only occur at the surface? Think about that. Why? Why does that only occur at the surface of your solution? So why does it only occur at the surface? So let's now look, if we had a particle a little bit further down. So now we have a particle that's a little bit deeper in our beaker of water. So here's our same beaker of water, and we have a particle that's deeper down. Now, let's say that it gets a bump to become a gas, right? It has enough kinetic energy to become a gas. Where's it going to go? Well, it's most likely going to collide with another particle and instantly become a liquid yet again, right? On top of that, these particles, the deeper you go, the more particles there are surrounding them and thus interacting. So if I look at the surface of our liquid, right, let's say we have that particle at our surface. So here's the surface of our liquid again, and we have the water molecule right now near the surface. Now, how many hydrogen bonds is this molecule going to have? Not as many, right? It's going to maybe have a couple going on. This is obviously not to scale, right? We have a couple hydrogen bonds going on, but there isn't the same level of interaction, right? So I'm going to say that this is a particle near the surface, whereas, all right, here's our particle near the surface. Whereas if we have a particle that's further down in solution, there's just going to be much more interactions. So here's our particle a little bit further down, and if it's a little further down in solution, right, there's going to be much more hydrogen bonding happening to our sad little water molecule here. Because it's sad because it cannot turn into a gas. It has more interactions, therefore it's going to require more kinetic energy in order for it to change states. Right, so our water molecule here is going to have a greater degree of interaction with the surrounding water molecules, and thus will not be able to change states. Does that make sense? Again, at the surface, less interaction. if you gain enough energy, you can leave and you're not going to be colliding with other liquid molecules. Whereas if you are deep down in the solution, you have more interaction because you're going to be surrounded by molecules. In addition to that, if you do happen to gain enough kinetic energy, you are going to likely collide and lose that energy. So this is why evaporation is completely a surface phenomenon. Alright, so now let's explore factors that affect the rate of evaporation. I already talked about one. Actually, I talked about two. The first one is in the example I gave you in relation to octane versus water. So IMFs have an impact on your rate of evaporation. Right? The greater your IMF, the more kinetic energy is required to overcome those forces, and thus the lower your evaporation rate. Right? My more volatile substance, the one with a greater rate of evaporation, is the one that has lower IMFs. I mentioned another one when I showed you the Boltzmann distribution, and that was temperature. The higher your temperature, the greater the proportion of molecules that have enough kinetic energy to change phases and enter the gaseous phase. On the flip side, you lower the temperature, you are going to lower the rate of evaporation. And lastly, we have surface area. The greater your surface area, the greater the rate of evaporation. Which makes perfect sense, right? It is a surface phenomenon, so the more surface exposed, the greater the chance that one of those high kinetic energy molecules can find themselves at the surface and leave and become a gas. So those are the three factors that affect your rate of evaporation. But let's now explore something a little different. What would happen if I took a beaker of water and I placed it into a sealed container? Right? So here I have a perfectly sealed container in which I have placed a beaker of water. Now at first, what's going to happen after I seal that lid? Think about it. What's going to happen? Well, at the surface, we're going to have particles evaporating and leaving, and we're going to have some condensing and returning into liquid phase. But at first, the rate of evaporation is going to be greater than the rate of condensation, right? The rate at which water is leaving is going to be greater than the rate at which it is condensing. Does that make sense? Right? There's not a lot of gas in this chamber yet, and thus there isn't a lot of particles in the air that it can collide with. Right? Those gaseous particles that have just left liquid phase, they're not as likely to collide with a particle and enter back into the liquid phase. So as time goes on, however, there's going to be more and more water vapor entering the air, and we're going to eventually reach a point at which our rate of evaporation will be equal to our rate of condensation, right? Once there's enough particles in the air, the odds of a particle leaving will be equal to the odds of a particle hitting another thing in the air and becoming a liquid. So, eventually, given enough time, our solution in our beaker will reach an equilibrium in our container, where the rate of evaporation will be equal to the rate of condensation. So at this point, your level of water in your beaker should remain constant, right? Because here, our water level would lower a little bit as more of it evaporated, but here it should remain constant within our container, right? Because the rate it's leaving and the rate it's coming back are the same. So your rate of evaporation is equal to your rate of condensation, and we call this a dynamic equilibrium, right? It's not that it's not changing. We have particles constantly leaving solution, but the rate at which they are leaving is equal to the rate at which they are coming back into solution. So this is a dynamic equilibrium. Now, why am I telling you all this? Why am I telling you all this? Well, that example I gave you, where you have your sealed container and eventually that liquid reaches an equilibrium, a dynamic equilibrium within that container, well, that is how we measure a substance's vapor pressure. Remember, gas pressure is going to be the pressure created by a gas impacting on the surroundings. So in this case, it's going to be the pressure exerted on the walls of your container. Vapor pressure is the pressure, the force per unit area, generated by a vapor in equilibrium with its liquid in a closed system, right? Where your rate of evaporation is equal to your rate of condensation. And this is a physical property, which means that it is something that is constant for any substance at a given temperature. So again, as your substance evaporates, it's going to hit the walls of your container and thus exert a pressure on them. And that pressure is going to be vapor pressure. Okay, so here I have two flasks. One contains water and one contains acetone. Now, water is very polar. Acetone is much more nonpolar. It does not have nearly the same IMFs that water has. So this device here will help us measure the vapor pressure of these liquids. If I attach the water flask to this apparatus, the height at which it pushes the water to will be representative of its vapor pressure. Same goes with the acetone. So what do you think will happen when I put the water compared to the acetone? Which one will have higher vapor pressure? Let's find out. So if I hook up the water, once it reaches equilibrium, it reads out at about 7 on our scale here. And again, the scale is fairly arbitrary, but it's reading out at 7. Now, what do you think would happen if I heated this water up? What would happen if I took this and I held on to it for a little while? What do you think would happen to the vapor pressure? Now, it's fairly subtle. You might not be able to see it on the camera, but it is slowly rising. The longer I hold this, the more it will rise to a point where it reaches equilibrium again. So it is slowly rising. Now let's try out the acetone. Alright, so I hook up the acetone, and now keep in mind the stopper did not go as far into this flask, so our starting point here won't be as high as it was with the water. It is reading out at just above a 7, so this does have a higher vapor pressure, but it is much more volatile. So what do you think is going to happen if I heat this one up with my hands? Well, let's find out. So if I heat this one up with my hands, there you go, it's shooting up pretty quick. So the acetone, being much more volatile, has a much higher vapor pressure, and the vapor pressure goes up more rapidly with increases in temperature. I actually have a beaker here just in case so it doesn't shoot out the top. So this is a beaker of ice water. Watch what happens to the vapor pressure when I stick it in this beaker. Huh. Oh shoot, we're going to suck with the other end. Oh no. Alright, so you get the idea. So your vapor pressure will change based upon your temperature, and the more volatile the substance, right, the lower the IMFs in that substance, the more vapor pressure it will exert. Now, vapor pressure is important for understanding boiling point. So, boiling occurs when vaporization takes place throughout the liquid and the temperature of the liquid remains constant. Right? When those phase changes are occurring, the temperature of your liquid will remain absolutely constant. Where's the energy going? Well, it's going into breaking the interactions in your liquid phase to become a gas. Now, the boiling point is the temperature at which the vapor pressure of a substance is equal to the external or atmospheric pressure. So if I had a beaker on this table and it was boiling, right, what's around me? Well, the atmospheric pressure is acting on that liquid, and therefore the vapor pressure being exerted by that liquid would be equal to or greater than the atmospheric pressure for it to be boiling. So let's quickly talk about boiling. Now, as you heat up a pot of water, what do you notice will start to form at the bottom of your pot? You might notice little tiny bubbles, And generally those little tiny bubbles form in the little scuffs and little crevices of your pot. And those little scuffs, those little brush marks, those are called nucleation sites. Right? If you have a pot and in the bottom there is a little tiny imperfection, well, it's going to be easier for liquid to become gaseous and maintain its gaseous state in these little tiny imperfections, because there's going to be less interacting particles around them, right? So you usually get these little tiny bubbles that can form in these crevices, and I'll do it in a different color here. And you'll notice these bubbles will leave and they'll rise to the surface of your pot as more and more liquid becomes gas. But as you're heating it up, before you reach the boiling point, you'll notice these bubbles don't really make it to the surface of your liquid. Why is that? Why is it that they'll kind of just peter out and die? Why is that? Well, that's because the vapor pressure inside of that bubble, right, pushing outwards, is less than atmospheric pressure. So the pressure pushing in on those bubbles is greater than the pressure pushing out, so they will collapse and become liquids yet again. Now, at the point at which we do begin to boil is when the vapor pressure inside that bubble is greater than or equal to the atmospheric pressure pushing on those bubbles. And then you'll start to see them rise to the surface and they will release those high energy gas particles into the air. So this is perhaps a much better illustration of the effect I'm talking about. So inside of your bubble, there are little tiny molecules of gas, obviously, right? Now, those molecules of gas are going to be hitting the sides of your bubble. Now, if the pressure they are exerting, the vapor pressure they are exerting, is equal to or greater than atmospheric pressure, the pressure pushing in on your bubbles, they will rise to the surface and your substance is boiling. If it is lower than the pressure pushing in on them, if it's lower than atmospheric pressure, those bubbles will collapse and shrink and they will not reach the surface of your liquid, right? They will not, your substance will not be boiling at that point. So, I always get asked a question, well, can't I just add more heat to make the substance hotter? Can't my water boil hotter if I add more heat? What's the difference in these two pictures here? Right? What's the difference in these two pictures? What's going on? Well, this is one where vaporization is happening much more rapidly. All we've done is we've increased the amount of heat here. So you can make your substance boil faster, but it's not going to boil hotter. So since boiling occurs when the force pushing out, right, that vapor pressure is equal to the force pushing in, if we decrease the force pushing on our liquid, right, if we decrease atmospheric pressure, we can boil at a lower vapor pressure. Right, if we reduce pressure, say we climb a mountain, we can reduce the temperature that is required for that water to boil. Now, we're going to go back to my initial demonstration I showed you, but you should now be able to figure out what's going on. Right? You should be able to figure it out. What happened when I poured the cold water on that beaker? On that flask, sorry. What happened? I condensed a lot of that water vapor above our liquid. Now, when I sealed it at 1 atmosphere of pressure, right? There was 1 atmosphere of pressure inside of that chamber, and when I cooled it down, in essence, by causing that liquid to condense, and by cooling it down, I drastically lowered the pressure felt on our liquid. And by lowering the pressure felt on our liquid, it was still really hot, it actually allowed it to boil. So I lowered the pressure exerted on the water until we reached a point where it would boil yet again. And if I put a beaker of water in a vacuum chamber where I can really reduce the pressure, you can actually get water to boil at room temperature. I'm going to link a video below where you can see that happen. So, what are some everyday applications here of what we've talked about? Well, cooking on a mountain. Let's say at sea level, water will boil at 100 degrees Celsius, sea level being 1 atmosphere of pressure. We call that the normal boiling point. Now, to hard boil an egg, it takes 10 minutes. If we went to the top of, say, Pikes Peak in Colorado, which has an elevation of 4,300 meters, on top of that peak, water would only boil at 86 degrees Celsius. Why? Well, there's less pressure being exerted on the liquid, therefore you need less vapor pressure to equal atmospheric pressure. Your water will boil at a lower temperature. So it'll take 20 to 30 minutes to boil the egg. These are just random numbers, by the way. And this is also the reason why Himalayan monks have better tasting green tea than you. Green tea tastes best when it's brewed in that 80 to 90 degree range, sometimes even less than that. And if you brew at a higher temperature, you extract more bitter catechins, so your tea just doesn't taste as sweet as it would if you boiled it at a lower temperature. Another one, pressure cookers are a great example. Think about it. A pressure cooker is a sealed container, and we are going to increase the amount of heat. What happens to your rate of evaporation if you increase the amount of heat? Well, it's going to go up, right? Your vapor pressure is going to increase. And what does vapor pressure here represent? As we increase the amount of gas above our liquid, we're actually increasing the amount of pressure felt on our liquid. So the way a pressure cooker works is by increasing the atmospheric pressure felt by your liquid. So it'll boil at a hotter temperature. In fact, it'll keep getting hotter and hotter and hotter and hotter until the device fails and it explodes. Right? That's why pressure cookers have those valves on them. You can set what pressure you actually want to cook your food at. So again, by increasing the atmospheric pressure, by increasing the pressure felt on your liquid, we are going to increase the boiling point. Thus, you will cook your food at a hotter temperature, and it will cook much faster as a result. Note, heating a boiling liquid more strongly, just going to remind you again, does not mean it's going to boil at a higher temperature, right? It's just going to vaporize faster. That temperature at which it will boil is constant for any pressure, right? For water at 1 atmosphere of pressure, it is 100 degrees Celsius. So we call that your normal boiling point. For any substance, when it boils at 1 atmosphere of pressure is the normal boiling point of that substance. So, comparing vapor pressures. If we have a low vapor pressure, what are some things we can say? Well, you probably have strong IMFs in your molecule. There's a low rate of evaporation. This is called non-volatile. These are substances that aren't very volatile. And they typically would have high boiling points. Remember, high IMF would also mean high melting point, boiling point as well. High vapor pressure on the flip side would be the opposite, right? Weak IMF, high rate of evaporation. They are considered volatile, and they will have low melting points and boiling points. So, since vapor pressure is a physical property, something that is intrinsic to your material, right? If you have water at 1 atmosphere of pressure will always boil at 100 degrees Celsius. If we lower the pressure to half that, it will always boil at some temperature. So we can graph that because for any given pressure, there will be a temperature at which that substance will boil. And these are going to be your vapor pressure graphs. Now, let's explore this in a little bit more detail. Let's ask a couple questions about it to help glean some insights into things like, well, what has the weakest IMF here? Right? What has the strongest? At what points will they boil? At what point would it boil if I changed the pressure? So, recall, when the vapor pressure and the atmospheric pressure are equal, they will boil. Anything less and the liquid will not. So let's explore water for a second. Here, remember, 1 atmosphere of pressure is 101.3 kilopascals. So water will boil. This is water here, and this is 101.3. If we trace that down, that is 100 degrees Celsius. If we look at something with a much lower boiling point, let's look at chloroform, for example. The normal boiling point of chloroform is right here, right? At 101.3 kilopascals, chloroform boils at, looks like 57, 58, something like that degrees Celsius. So all I'm doing is I'm just tracing down to our x-axis to determine what my normal boiling point is for these substances. So, right, there's water's boiling point and there's chloroform's boiling point. Now again, there's only 2 ways you can affect the boiling point of a substance. You can change the temperature to reach that boiling point, or you can change the pressure. Now, if we decrease the pressure felt on our liquid, we can decrease the boiling point. If we increase the pressure felt on our liquid, we can increase the boiling point. So, for example, let's say I want to boil chloroform. Let's say the pressure experienced on it is 70 kilopascals, right? So chloroform is experiencing a pressure of 70 kilopascals. At what temperature will it boil? So all I have to do is look 70 is right here. And I'm going to trace across, well, there's 70 on our chloroform line. And then if I trace down to our x-axis, we see that it is 50 degrees Celsius. So chloroform will boil at 50 degrees Celsius when the pressure is 70 kilopascals. So let's look at a couple other examples here. Let's say, let's take acetic acid. Okay? Now if I said your substance is boiling at a temperature of, let's say, 70 degrees. Okay, so the normal boiling point is like 118-ish, it looks like. What about at 70 degrees? What would the pressure have had to have been for it to boil? Well, at 70 degrees, if we trace that up, right, we see that it would have boiled at this pressure right here. And if I trace that across, it's about 18 kilopascals. So what about water? Let's say we wanted to make water boil at room temperature. So room temperature, 20 degrees Celsius. Here's water here. We would have to decrease the pressure to approximately 2.5-ish kilopascals. So you can boil water at room temperature if you can get the pressure it's experiencing low enough. So this was a lot to take in. Please attempt the practice questions and let me know if you have any questions.